Hi, so here I'm going to work out example number 3 for curve sketching that we weren't able to do in class, but I think it's still good practice, so I hope you've tried it out yourself, but I'll walk through all those steps now. Okay, so we've got this function f of x, and we're looking at it specifically for the interval of x going from negative 2 pi to pi. I'm just going to move this, doesn't matter. Okay, so let's start off by calculating the derivatives, because we know we'll need to use those. So f prime should just be 1 minus 2 sine x. And then the second derivative we can see is negative 2 cos x. I did mention before that the derivatives for this kind of question for the exam will be given to you, but you know, it's always good to do them for these examples. It's still something you need to know how to do. All right, so step 1, we're looking at domain and asymptotes. Well, because f of x is just like a polynomial and trig function, it's not going to have any domain restrictions and no vertical asymptotes. Polynomial and so no, or I guess we can just say domain of f is all real numbers and no vertical asymptotes. For horizontal asymptotes, we have to look at the limit as x goes to infinity of the function, but we'll see that as x goes to infinity, that x term is just going to blow up to infinity as well. And same thing as x goes to negative infinity. That 2 cos x part is never going to really contribute anything, because 2 cos x will always be between negative 2 and 2. So here we can see that we have no horizontal asymptotes. Okay, that's not too bad. Now let's move on to our second step, which we know is to find intervals of increase and decrease. Well, if we look at our first derivative, we want to find the critical numbers. So we've got f prime, as shown above, is 1 minus 2 sine x, and that is equal to 0 when 2 sine x is equal to 1, and so sine x is equal to 1/2. This has a lot of solutions, actually, because remember, we're looking at going from negative 2 pi to pi. And so if on the unit circle, the angles with a sine value of 1/2 are here and here, so this one would be the one that we would normally just consider as pi over 6. And then this one here is 5 pi over 6. Because we're going from negative 2 pi to 2 pi, we also have to look at what we would call these angles if we were going in the reverse direction. So here it's like we're going negative, 6 pi over 6, and then we go 1 extra. And so that means then our angle that was 5 pi over 6 is coterminal with 7 pi, or negative 7 pi over 6. You know what, I'm going to delete, just erase that so it's hopefully more clear. So this angle here that we get that's coterminal with 5 pi over 6 is negative 7 pi over 6. And then if we want to see the one that's coterminal with pi over 6, so going this way, we can see that this one would be negative 11 pi over 6. Now you could also just take these angles and subtract 2 pi and see that that's how exactly we get those same numbers. But I find it helpful, I guess, to understand why that works, you know? All right, so that means our numbers that we need to consider are Let's put them in order. So we've got negative 11 pi over 6, negative 7 pi over 6, pi over 6, 5 pi over 6. And because f is just x plus 2 cos x, f is differentiable everywhere. So no other critical numbers here. All right, let's make our table then. So this is sign analysis on the derivative. Okay, let's see, lots of intervals, because now I'll have to go from negative 2 pi to 11 pi over 6, then negative 11 pi over 6 to negative 7 pi over 6, then negative 7 pi over 6 to pi over 6, then pi over 6 to 5 pi over 6, and finally 5 pi over 6 to 2 pi. Remember, we're only sketching this one between negative 2 pi and 2 pi, and so that's why I didn't say negative infinity and infinity on those last and first intervals. Okay, well, here we don't really need to factor what our f prime was. It's 1 minus 2 sine x. And we now want to see where that is positive and negative. Now, to figure this one out, what I do is I'm going to draw another unit circle. And if we think about where 1 minus 2 sine x is going to be positive on the unit circle, well, that means then that if we kind of move things around, that's where sine x is now less than less than 1/2. And that then on the unit circle is where your y value is less than 1/2. So that means that this part of the unit circle corresponds to all of the angles where f prime is positive. And then this part is where f prime will be negative. And the place where it changes is exactly where we saw that sine x is equal to 1/2. So if we're just using, like the first lap around the unit circle, we know this was pi over 6. And this angle was 5 pi over 6. So then, now when it comes to going back to our table and determining when 1 minus 2 sine x is positive or negative, we can actually just consult this. So, and actually, yeah, I'll use like the laser pointer, that'll be good here. Okay, so for this first interval, that's negative 2 pi to negative 11 pi over 6. So remember, negative 2 pi is the same as 0, and we're kind of moving backwards. So that's this part here, that's in the blue, that means this is positive. You know what, I'll use blue there. If you're colorblind, let me know also, by the way. I've been trying to make sure that what I do is like colorblind friendly, but sometimes I forget to do dotted lines and stuff. But yeah, this corresponds to this part here. Then we've got negative 11 pi over 6 to negative 7 pi over 6. So this is negative 11 pi over 6. And then to negative 7 pi over 6, that's exactly this part here, where we saw that f prime is negative. Then for the next one, now you can kind of see what's going on here. This negative 7 pi over 6 to pi over 6, that's going from this angle all the way up to here. And so again, this is just the whole blue lower part where we see that f prime is actually positive. Then between pi over 6 and 5 pi over 6, again, we see that that's where we get negative f prime. And then from 5 pi over 6 to 2 pi, we finally get back to positive. So then that means that our function f is increasing, decreasing, increasing, decreasing, increasing. And this also means then that we've got local maxes and mins essentially at every critical number because it's always changing. So that's nice. So here, this tells us that we have a, or maybe I won't do arrows, that's a lot of arrows. Okay, so here we can see that we have a local max when x is equal to negative 11 pi over 6. The y value is f of negative 11 pi over 6. I won't work out the intermediate step, but you can double check that that ends up being negative 11 pi over 6 plus root 3, whatever that number is. Now later on when we're sketching, we'll have to kind of make a guess, and I'll show you what we'll do for that. Okay, so then at negative 7 pi over 6, it looks like we've got a local min. And then the y value there is f of negative 7 pi over 6, which works out to be negative 7 pi over 6 minus root 3. Okay. Then our function is increasing again until we get to another local max. That corresponds to when x is pi over 6, and then y will be f of pi over 6, which ends up being pi over 6 plus root 3. Finally, our function is decreasing again until the local min we have at 5 pi over 6. And our y value there is equal to 5 pi over 6 minus root 3. Awesome. Okay, so that's all we need to do for the first derivative. Oh yeah, I guess this was step 3. I'll label that there. Cool. Well, we'll use that information again when we're sketching, but now we can move on to the second derivative and look at our concavity and if we have an inflection point. So, as we saw above, the second derivative is equal to negative 2 cos x. We want to see where that is equal to 0. Well, that's just where cos is 0. And so, within the interval from negative 2 pi to 2 pi, that means we've got negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. Okay, so now we've got 4 numbers to consider when it comes to making our table. Maybe I'll move this to the side a little bit. Oops. So here we've now got 5 intervals. So there's negative 2 pi, negative 3 pi over 2, negative 3 pi over 2 to negative pi over 2, negative pi over 2 to pi over 2, and pi over 2 to 3 pi over 2, and finally 3 pi over 2 to 2 pi. Okay. So for this one, what I'm going to do, just because, well, I don't know, I'll show you how I thought of this one before when I was first looking at it. If I just think about what's happening with cosine, then I know that our second derivative which is negative 2 pi cosine. We'll just have the opposite of that. It's negative 2. Did I say pi? I just meant negative 2 cosine. So that's our f double prime. And then we can see what that means about f. Okay, so from negative 2 pi, so this is 0 or pi. Oh, I don't know. I guess we don't say equal, but it's a coterminal angles. So this is 0, this is 2 pi, negative 2 pi. Here, this is pi over 2, but it's also negative 3 pi over 2. So from negative 2 pi to negative 3 pi over 2, that's this first quadrant. That's where cosine is positive. So negative 2 cosine is negative. And that's how I'll be going about this, is I'll just, look at these intervals. So negative 3 pi over 2 to negative pi over 2. So down here we've got 3 pi over 2 and negative pi over 2. This is where cosine is negative, and so our second derivative is positive. Then we've got negative pi over 2 to pi over 2. So that's quadrants 4 and 1. Cosine is positive again, so our second derivative is negative. Then we've got pi over 2 to 3 pi over 2. Cosine is negative there. Second derivative is positive. And then finally for 3 pi over 2 to 2 pi, that's quadrant 4. That's where cosine is positive, so the second derivative will be negative. So that's quadrant 4. Maybe I'll write these in just because that's kind of helpful. So this is quadrants 4 and 1. This one was quadrants 2 and 3 again. And this is quadrant 1. Okay, cool. So now that we have that, we can say then that f is concave down in quadrant 1, concave up, and then it's concave down, and then up, and then down again. And based on this, we can say that we have a bunch of inflection points as well. Because we seem that we change concavity at every new interval, so those numbers that we found above as solutions to where the second derivative is 0, those will all give us inflection points. Or points of inflection, same thing. Okay, so we've got x is negative 3 pi over 2. If you work out what your y value is, remember you use the original function for that. We also get negative 3 pi over 2. Just because here, if you think about it, the original function has that cosine, so you just end up getting the same value back, but you can plug these in, you'll see. So x, negative pi over 2, the y value ends up also being negative pi over 2. When x is pi over 2, y value is pi over 2. And when x is 3 pi over 2, y is 3 pi over 2. Awesome. Okay, so now what we can do is get our sketch going. So I'm trying to think of the best way to kind of keep all this information and work out some of it. Maybe I'll copy and paste and then like shrink just to kind of keep it small. Okay. Then the concavity, I guess I'll copy this table. This is probably not very fun to watch, but I'm sorry, I've got to do this. Okay, so I'm going to just work out what some of the y values are as decimals, roughly, just to kind of estimate. Let's see, so for our first local max, this negative 11 pi over 6 plus root 3, I'm going to use that root 3 is roughly 1.7, so negative 11 pi over 6 plus root 3. Well, I'm going to pretend for the purposes of this that pi is 3.1, and then negative 11 over 6 pi is like negative 2 pi-ish. So we're going to say that this is roughly negative 6.1 plus 1.7. So I guess 4.5, 4.4, negative 4.4. Okay, and then negative 7 pi over 6 minus root 3. So that's roughly negative 3.1 minus 1.7. So negative 4.8. This one, okay, so if we've got pi over 6, then that means that, and we're saying that, like, pi is roughly 3.1. Let's say pi over 6 is about 0.5. So that means this is about 2.2. And 5 pi over 6, I am going to just round up to being pi. And so then here, this is like pi minus 1.7. So 3.1 minus 1.7, 1.4. Good enough. Okay, so now we can put those local maxes and mins down. I'm going to color code what we've got. So, or maybe I'll use symbols. Okay, so for the local maxes, I'm just going to use plain dots, and for local mins, I'm going to use X's. So first, we've got the local max at negative 11 pi over 6 and about negative 4.4. So negative 4.4, 11 pi over 6. I mean, maybe I can fill this out a little bit more. So maybe let's say negative 11 pi over 6 is about there. 4.4 is about there. Negative 4.4. So this is our first local max. Then we had a local min at negative 7 pi over 6, and then y is negative 4.8, so slightly lower. Oops, that's supposed to be an x. So like here, okay. Then we had local max at pi over 6, 2.2. And a local min at 5 pi over 6 and 1.4. So let's say there. Okay. And we already know based on the table too that will be like how our function will behave between. So we know that we're increasing and decreasing in certain intervals, but we also want to take into account the concavity. Okay, let's put down our inflection points then. So these ones, copy and paste as well, actually. Let's see, I'll use a square. I don't like that it's hollow. I'll fill it in. Okay, so negative 3 pi over 2, and y is negative 3 pi over 2. 3 pi over 2 is, like, let's say it's, yeah, like 3.1 plus like 1 point, or let's do the thing where we say that pi is 3. So it's 3 plus 1.5, so 4.5. So we have negative 4.5 and 4.5. So here, this is our first inflection point. Then we also had one at negative pi over 2, negative pi over 2. And again, we're going to say that negative pi over 2 is about 1.5. So we have this inflection point here. Then we had another one at pi over 2 and another one at 3 pi over 2. So pi over 2 and 3 pi over 2. So that's 4.5 we said. Wonderful. Okay. So now we're ready to connect. So let's see what happens in this very first piece. So we know that we're going to be increasing starting from negative 2 pi. And the first important number that we hit is at negative 11 pi over 6. So from 2 pi, we're increasing, and we can see that we're concave down. Then from negative 11 pi over 6, we should start decreasing until we hit the local min that we marked with an X. So we're decreasing. But now that we've hit the square, we've got to be concave up. Good enough. Okay. So we're still concave down, now we're concave up. Now we just increase until, and still concave up, until we hit that next inflection point, which is where we'll now be concave down. And just keep increasing until the local max there. Then decreasing, and then inflection, and then increasing after the local min. Do I have like a dead spot there? There we go. Increasing, so here we're concave up, and then, I don't know, however that goes, but now we're supposed to be concave down, so I'll draw that a bit better. And that's it. That's our function. So that one's a bit trickier, I think, just because there are so many numbers to look at. But it's still totally doable. We can just use some estimation just to make sure that we're putting things in the right order. Yeah, let's look at the actual function, because I did again graph it, and we can see that, yeah, that's the same kind of behavior that we've got here. Just a little smoother. So yeah, hopefully that helped. I'll put a link to this YouTube video in the notes where I upload this. So yeah, thank you for watching.